Hello, yet another DPP of atomic structure. Now it is related to spectrum Bohr model. So let us continue, read all the questions, attempt them, then we will see the hint and then we'll have full solutions. The first question says, identify the transition corresponding to the minimum wave number among the following. So there's a diagram, identify that. Now let's see the solution. We know that Lyman energy has the maximum, Lyman series has the maximum energy, followed by the Balmer, then the Passion, and then the bracket, and then the Fund series, right? So this is the energy decreasing sequence for various series. So you can see Q and R are Lyman photons, so they must be having high energy, right? And P and S are Balmer photons, but P has less energy. So P has the least energy, and we know one thing, that energy and wave number have direct relationship. Hc wave number is basically equal to energy of photon. So surely P has the minimum wave number. That's wonderful. Question number 2. The wavelength of the second line corresponding to the Balmer series of H atom is. See, it's a simple application. You just have to visualize what is happening in the Balmer series, and it is asking about the second line of Balmer series, right? So let us write some orbits. First orbit, second, third, and fourth. So this is the destination of Balmer series, and we have to come second line, come from 4. Now it is asking the wavelength. So we know that wavelength can be written like this: 1 upon wavelength is the wave number, which is equal to R Rydberg constant into 1 upon 2 square minus 1 upon 4 square. So if you solve this, you will get R into 1 by 4 minus 1 by 16, that is 3 by 16. Wavelength is just the inverse of this, 16 by 3R. That's B option. Now let's come to the question number 3. The number of photons belonging to the Balmer series of H, when we consider all the possible d excitations from n equal to 6. See, now let's have the visualization. Let us draw all the orbits it is talking about. 6th orbit, then you have the 5th orbit, then you have the 4th orbit, then 3rd orbit, and we have to stop at 2 because we have to consider only Balmer photons. Now you see the possibilities of Balmer. So remember that in Balmer you have to jump to 2. Wherever you jump from, you have to jump to 2 only. So jumping to 2, that means destination 2. There are how many possibilities? You can clearly see. There are 4 possibilities. So that's the amazing answer, D option. Now let's come to the final question. If the energy of photon for the first line of Lyman in H is E, then the frequency of photon for the first line in Balmer would be. See what it is asking. It is basically giving Lyman as well as Balmer energies. So let us first of all visualize them. So these are the 3, first, second, and third orbits. Now the line corresponding to the first line of Lyman series is this. If this has energy E, then it is asking the frequency of this, right? So let us do this. Let us apply this formula. If energy is E, then we know that this is corresponding to 1 minus 1 by 4, right? This thing is corresponding to E. And this is 1 by 4 minus 1 by 9. That is equal to 5 by 36. So if you take the ratio, then 5 by 36 and 3 by 4 will also have a ratio. So you will end up at 5 by 27 something. And you also need Planck's constant, right? So there is another method if you want to try. You can say this is 13.6 into z square, that is 3 by 4 is basically equal to E. So you get the value of 13.6 from here, which is equal to 4E by 3, right? Now you use 13.6 this in this. So if you multiply 5 by 36 into 4E by 3, then you'll get 5E by 27. But that's the energy of photon. So we need frequency. So you have to divide by H only. So that's the option B. So this is the amazing revision of spectrum and Bohr model. Thanks a lot.